Hello, this is Alfonso Lanaverde for lab03, the magnetic field of a bar magnet. Try and get this done really quick because I need to upload this ASAP. So, let's move on. So the intro. The purpose of this lab is to find the distance dependence of the bar magnet's magnetic field compared to the Biot-Savart law. And here are the concepts. So we have Biot-Savart's law, which is the following equation, which we mathematically compute using the code. And then we have the linearization, which is ln of bx equals ln k plus n ln r. And then the distance dependence formula, which is b bar is equal to krn. So the preview is now I use some heavy rounding here, but n is negative 2.5 and umag is umag is 3.4 am squared. So the setup. So we do two different things. We need the on horizontal and then the perpendicular. So for the on horizontal, we find magnetic north using our phone, and then we find the magnetometer chip on the phone, and then we slide the phone on the meter stick until the magnetic field equals the XL value, and then you record the distance. So for dperp, you record the Y component, and then move your phone along the second meter stick, just like in the third image, until you get the equivalent perpendicular distance from one side to the other. And then from there you find the XYZ of the magnetic field, and then you adjust it for the Earth's magnetic field. So some observations were that for the first one, which was true, that the further away you get, the magnetometer reads closer to zero in the X direction. And then for the last one was true, that the magnetometer's X increases as you get closer to the, as you move the phone closer to the experiment. So other info, the system was the bar magnet, the surroundings would be everything else, and we model the bar magnet as the biomagnetic dipole. Our assumptions are that we only account for the magnetic fields of the Earth and bar magnet, and because of that, we have some sources of error, which would be that the assumptions simplify the model and removes forces that can be unaccounted for, because there could be more magnetic fields acting on our bar magnet, and there could also be human or technological error, like, oh, I did my math wrong because I was rushing to turn this in on time, or the technology like the magnetometer just wasn't very good, stuff like that. So our code. If we go ahead and take a brief look at that, let me pull up the page. We have the following formulas, which is we use our umag that we calculated at 3.4, and then you edit the distance value, and then the rest does basically what it tells you. So then when you run the program, or because we were given sample code, you get this mess of forces, but we get our dperp is equal to 0.277, and then we also get the vectors for B, and then we get the magnitude for B also. This again, swap view. So what does it mean? What if you hadn't oriented, or what if and what does it mean? What if you hadn't oriented your presentation to compensate for magnetic north and instead laid out your meter stick at some intermediate angle with respect to it? We would just get different values, quite simply. The intermediate angle might not exactly be what we compensated for X, or for X being Earth's magnetic field, so our results would obviously just vary by how far off we are from the Earth's magnetic field. And then what if you were to stick two identical magnets together end to end and run the experiment again, and you think your measurements would differ? So if they were end to end, our forces would be larger but in the same direction, because it'd be like two vectors with the same X, and that X doubles, or not exactly, but you get the point. It just means a larger X magnitude in the same direction. And that's my quick experiment. Thank you guys.